Hello everyone and welcome to the Big Bang. Here I am going to show you a quick drill to go over any time you need to find an input or output impedance or even a transfer function and you are presented with a voltmeter, an ammeter, a driver, or a current or voltage source. This is quite handy to keep in mind and should save you some time solving problems. Essentially, it all boils down to what is the ideal impedance of that element. There is already a video discussing the ideal impedance of different inputs or outputs. Thus, if you are curious about that, you can check out that video. Here, we will be using those ideal impedances to simplify a circuit. Let's first establish a few key concepts. Remember that a circuit may present itself with either a voltmeter, an ammeter, a voltage source, or a current source at its input or output. These inputs and outputs will simplify differently, all depending on the ideal impedance of that element. For example, since the ideal impedance of a voltmeter is very large, the voltmeter can simplify to an open circuit. And since the ideal impedance for an ammeter is quite small, near zero, the ammeter can simplify to a short circuit. The same idea follows with sources. If the source has an impedance near zero, it simplifies to a short circuit, and if it has an impedance near infinity, it simplifies to an open circuit. Now, let's put this knowledge into practice by looking at an example. Picture this circuit. We have a current source in parallel with a resistor, then we get a dependent current source in parallel with another resistor, a capacitor, and an ammeter. This can look a bit intimidating, but we can break it down to manageable pieces. We can name these R1, GVN, R2, and C for the capacitor. The game here is to find the input and output impedances of the circuit. Remember that to get the input impedance, we are looking at the circuit from the input perspective. And to get the output impedance, we look at the circuit from the output perspective. From the input perspective, we get the first resistor, the dependent current source, the second resistor, the capacitor, and because of what we have learned to the left, a short circuit. The fact that this ammeter simplifies to a short circuit will greatly simplify the circuit. The electrons will all ignore the resistor and the capacitor in parallel and circle around them. Effectively, the only thing affecting the input impedance will be the first resistor, which is the last impedance left after the simplification. Thus, Zn equals R1. Now, from the output perspective, we have an open circuit because of the large impedance from the current source. Then we have the first resistor, the dependent current source, the second resistor, and the capacitor. Because of that open circuit, no current will run through the first resistor. But what about the current running through the dependent source? Note that the dependent source is listed as G times Vn. Because of that open circuit, Vn is 0 on the left-hand side of the circuit because the input current would be 0. This makes the dependent current source 0, and we can also claim that it will not affect the output impedance. This means that all we have left now are the second resistor and the capacitor in parallel. To calculate the output impedance, we then have 1 over j omega c in parallel with R2. That's basically R2 times 1 over j omega c divided by R2 plus 1 over j omega c. The output impedance then simplifies to R2 over 1 plus j omega R2 times C. And outputs of the circuits. All right, I'll see you next time.